Okay, so just to let you know, when we solve these differential equations using power series, I will typically allow you to stop here at the recurrence relation. Okay, and so the book asks you to write the full polynomial out, and in fact, it asks you to find two functions, y1 and y2, such that y1 and y2 would be a fundamental set of solutions. And actually, if you know what the recurrence relation is, you can do that pretty easily. So for example, you could set a0 equal to 1 and a1 equal to 0 and find one function, and then you can flip that, take a0 equal to 0 and a1 equal to 1, and then find y2. And so that's how you would normally find y1 and y2 if you wanted to. Okay, so so just to give you an alternative method that we're going to take a look at now, we're going to find we want to find the solution to a differential equation using a power series, but notice that that really means that you're just trying to find an expression for the coefficients a sub n, right? And by the Taylor formula, we know that a sub n is related to the derivatives of your solution, right? And so if I could find expressions for the nth derivative, or an expression for the nth derivative of the solution at a point, then I would know what the a sub n is, right? And this is going to be called the derivative method for solving the differential equation. So it's kind of weird to discuss it. Let's just see if we can go for it and see if we can figure it out as we go. So here's the same differential equation that we just had. We're going to try using the derivative method to find the first 5 terms of the Maclaurin series for y of x. Right, so I would just note that the solution then would look like this. Right, that's just writing out the power series. And then do we know a0 and a1? Yes, we do. a0 is y of 0 and a1 is y prime of 0, so those are your initial conditions, and we'll just leave those generic as usual. Okay, and so now what we want to do is we want to try to figure out what y double prime is at 0, because that's the next one up. And you'll notice that if you look at this equation, we can just solve this for y double prime and then evaluate everything at 0. And so here we go. We just move everything over to the other side, and now you can evaluate each of these functions at 0. And so you get y double prime of 0 is equal to 0 times y prime of 0 plus y of 0. And we remember that y of 0 is equal to a sub 0. So therefore y double prime of 0 is equal to a0. Good. Good so far. So now, can we figure out what y triple prime is? Well, notice that right here, you know what y double prime is. We can just differentiate this, right, to find out what y triple prime is. So we differentiate both sides, and the only trick to this process is this thing right here in the middle. Remember to use the product rule. This is a product rule function, or a derivative. So let's see how that would work. So y triple prime is going to be xy double prime plus, and then the derivative of x is 1 times y prime, right? Then you have another y prime, so if you add those two y primes together, that's how we get the 2y prime. So remember to use the product rule on the xy prime. And so again, that was xy double prime plus 1 times y prime. And then the other y prime came from this other term. Good. So now that we have that, now we just evaluate everything at 0, just like before. And so again, we get 0 times y double prime of 0 plus 2y prime of 0. Do we know what y prime of 0 is? There it is, a1. And so therefore we simplify to just 2 times a1. Good. So we just keep doing this over and over again. Keep differentiating over and over again, over and over again. So here we go. The fourth derivative is equal to, remember to use the product rule, xy triple prime plus y double prime plus another 2y double prime from over here, so you get 3y double prime. Okay, so again, that was the product rule on xy double prime, is why the 3 popped up. And so evaluate everything at 0, and so we get just 3 times y double prime of 0 which is, let's see, 3 times I double prime is 3 times A0. Good. Now we only wanted the first 5 terms. The first 2 terms are already given, and so y double prime will give us the term for x squared, y triple prime will give us the term for x cubed, y to the 4th will give us the term for x to the 4th. So we've got our 5 terms now, and so let's see if we can write those down. A2 is going to be equal to y double prime. Did you remember to divide by 2? Alright, so A2 is actually y double prime divided by 2. A double prime we found was A0. Okay, now A3 is going to be what? Y triple prime divided by 3 factorial. And then we found what y triple prime was, 2A1. So we put that in. And now notice that the 2's cancel, and so you're just left with A1 over 3. And so now we look at A4. A4 is going to be the 4th derivative divided by 4 factorial. Okay, and so we found that A4 was 3 times A0, so I'm going to put that in at the numerator. And then the 3 in the numerator cancels with the 3 in the denominator from the factorial. And so that just leaves you with a 4 and a 2 in the denominator. Right, and so we end up with A0 over 4 times 2. And so you can see what's happening, right? In fact, what will A5 be? Can you tell? A5 is going to be similar to A3. A5 is going to be A1 over 5 times 3. And then A6 is going to be A0 over 6 times 4 times 2. Okay, so you get the picture. Okay, and so now that we found all these coefficients, right, we can plug them all in and write down the solution. Very good. And notice that now the solution does look like the solution that we had before, except I factored out the A0 and the A1 before. Okay, good. So this is the same solution that we had, and so now we have 2 methods for finding a power series solution to a differential equation. The first one is to just find the recurrence relation by using the summation index. Right? We manipulated all the sums into one sum, and then we set the coefficients equal to 0. And then that was how we found the recurrence relation. The second method now is just to compute derivatives. And this one's a lot easier to do often. It kind of depends, right? We had some nice functions here to work with, so that made it easy to differentiate. Okay, and then we'll look at more examples. The hardest part of this first method, though, is the algebra. Okay, and so we're going to go back into that in the next example and set things up. So I'll just leave you here, and we'll start a new video to start this fresh. But is this the same problem that we had before, or is it a different problem? Do you see that the base point is different? And so this little change right here is going to make a big difference in how our algebra works. And so you'll see that in just a second. Yeah, so the idea here is now that our index, or our power series, looks very different than what we had before. Before we just had a sub n x to the n, and we were able to deal with this middle term pretty easily. So that's a little bit of foreshadowing to the next video, and we'll see you then. We're going to solve this differential equation in the next video. Why is it not stopping? Stop! Stop!